Temperature and pressure dependence on Henry's constant. We got started with that yesterday, looking at the temperature dependence. And what we were able to show was that it has a functional form where the logarithm can be expressed as a constant minus another constant over the absolute temperature. And if we look at the data set that I provided you, for a number of the cases, you're given data at a variety of values of temperature, and if we plot them up, it bears this out fairly well. This is a case of ethylene acetone, which shows a beautiful correlation here. You can see the data points as I've written them here. They're not always that good, but it's usually acceptable, unless we have some reaction, chemical reaction between the solute and the solvent, as we would have for the case of carbon dioxide and water, or say ammonia and water. So let's assume that the issue of the temperature dependence of Henry's constant here is resolved, and we see that it is fairly significant. So let's look next at the pressure dependence. And here I'm going to give you the result, which can be derived, but I'm not going to derive it for you. I'm just going to state it, that the partial of Henry's constant here, if I can write it in a decent way, at constant temperature is equal to, let me write it and then I'll talk about it. Where that numerator is the partial molar volume of the solute 2 dissolved at infinite dilution in the solvent 1. So, and if you just look at the notation for it, it's evident that that is what it is referring to. We can think about this right now a little bit before we do anything else, and that is that this is like a liquid molar volume. So that gives us an idea of the order of magnitude. And if we're talking about gases, those are relatively small molecules, so that would usually be something between 20 and maybe 80 or so cubic centimeters per mole. And remembering what R is in those units, that's 83 or so, and temperature maybe 300 or so, it's evident that this is a fairly small quantity. But if we integrate it, it looks like this. Let's say Henry's constant at some pressure that we're interested in would be equal to Henry's constant at some pressure P0 times a pointing factor correction, which is then exponential of this where P0 here refers to the pressure for which we have the data for Henry's constant. And we have a number of data. We can take a quick look at that, assuming I can find them here. So you'll notice that if I look up here, this is Henry's constant given in units of atmospheres, but this little thing indicates that this is for a total pressure of 1 atmosphere plus whatever solvent saturation pressure there might be. In other words, that's the partial pressure for component 1, which is a solvent. That's usually going to be pretty close to negligible. So this is our database, and P0 then, for our situation, is 1 atmosphere.
That whole chart is for a solvent partial pressure, and you said that's negligible?
I didn't say it's always negligible, it's generally negligible, but there are situations when it might not be.
Okay, so if we're,
This is Henry's constant for a pressure of 1 atmosphere plus whatever that solvent partial pressure would be.
Oh, okay, I see.
That's what I just said.
All right, yeah.
So if we take a look at this, so we can see that the corrections are not going to be of any great significance unless we are at high pressure, but of course there are some situations where we are at high pressure, so it would be important. And just to get an idea of that magnitude of the correction, I plotted it up. So here's the pointing factor for Henry's constant. If we make the assumption that this partial molar volume at infinite dilution of a dissolved solute is 50 cubic centimeters per mole. And here's our reference pressure, P0 of 1 atmosphere, and let's take the temperature at 25 degrees centigrade, which is 298.2 K. So this is the pointing factor. That would be the correction factor, the one that by which you would multiply the the values that you get out of the table. And as a function of the pressure here, you see we can go all the way up to 50. This is in atmospheres, 50 atmospheres with only about a 10% correction. So I think that we don't need to say much more about that. It's pretty straightforward how you handle it if you wanted to get a Henry's constant at some other conditions here of temperature or pressure.
Is P0 different than the one in the other pointing factor? Because in the other pointing factor, it was,
It's whatever the reference is. So it might be different if you have a different reference.
because it was the saturation pressure.
Yeah.
Okay, so that was the reference.
So our reference is the pure liquid.
Okay.
So our next order of business here, an important one, is deviations from Henry's law. So if I make a plot here, Henry's law, and the plot is going to be the fugacity here of that component in the liquid phase plotted against the mole fraction. We got 0 here. And Henry's law says that we have at low enough x2 we have straight line behavior. And that'll take us up to, as I said before, something of the order of 0.03 mole fraction, but that should be just a rough approximation. It would be different in different cases. But when we get above that, then it's going to start to deviate away. And maybe that's a little bit too much deviation, because at first here it's fairly slight. So this suggests what we have. So this would be my Henry's law behavior. And here would be what the actual fugacity would look like as a function of mole fraction. We get above the range of concentration where, where Henry's law is expected to be valid, which is in very rough terms about 0.03. So in a formal way, we can describe that by putting in a correction factor, just like we did for deviations from Raoult's law, for example. So I can write down the fugacity here of the component in the liquid phase equal to an activity coefficient times mole fraction times a Henry's constant. And we can refer to this as a modified Henry's law. If I can write it appropriately here. So this activity coefficient is and what's the important thing to notice is it is not equal to the old activity coefficient, because we're referring to a different reference state. So we might ask ourselves, is there anything we can say about correlating this correction factor for Henry's law? There is. There are theories of dilute solution that can give us a description, and they kind of look a little like a virial expansion, but what you will often see is something like this. Let's see. And that would be the leading term in what could be a power law type expansion. And K here is some constant obtained by data. But the functional form here has theoretical validity, and if we have a value of K, that generally will take us to x2 somewhere between 0.1, maybe up to 0.15. So that will bring us up to a higher range accordingly. Beyond that, we probably should use some other method to describe the system and not refer it to Henry's law. So this is probably going to cover the range of interest to us if we're talking in the context of Henry's law. So let's make an important summary here. We've got Henry's law. For dilute solutions, let me rewrite it here so I can conveniently make a comparison. And then we've got, for ordinary solutions, we've got the Lewis and Randall rule. Which says that the fugacity is equal to mole fraction times the fugacity of the corresponding pure component. So what we've got here is what we might call an ideal dilute solution. And this is simply an ideal solution. Ideal dilute solution holds as x2 goes to 0, and the Lewis and Randall rule holds universally as x2 goes to what? Goes to 1. So it's important to look at these distinctions, but let's graph it up and now graph both Henry's law and the Lewis and Randall rule for a particular case and see where we are. Let's see if I can make a clean drawing here. I'll plot the fugacity here against the mole fraction running me from 0 to 1. And if I have Henry's law holding, that's going to hold here at these very low concentrations as x2 goes to 0. Then I'm going to have a straight line that looks like this, but it will start to deviate away. But if I extrapolate this whole thing, let's see if I can do that. Make it a little bit nicer. It would look like this. And the value up here, if I extrapolate the Henry's law all the way up to a mole fraction of 1, this intercept is going to be Henry's constant. Now if I plot the Lewis and Randall rule, that would be this one. Then what I'm going to get is, let me just plot a line for that. Make it a little bit lower. So, Henry's law. This is the Lewis and Randall rule. You can read that. So what is this?
The fugacity of the pure component.
That's my pure component fugacity.
Yeah.
So it's interesting that we have this Lewis and Randall rule is being obeyed as x2 goes to 1. So if I were to plot from this end, it's going to look something like this. In other words, this is going to merge with that as I get to a near unit mole fraction for my so-called solute component. So I've got this behavior down at this end, this behavior at this end. So if I were to plot the whole thing, it might look like this. So here's my Henry's law, here's Lewis and Randall rule, here's the actual behavior. But it asymptotes at one end to Lewis and Randall rule, at the other end to Henry's law. And this is a universally true qualitative diagram. So what we've got here are actually two standard states. This is our ordinary, we call it a standard state, so it's referred to as the solvent standard state, namely the pure component. But here we've got a more interesting thing. This is what we would define as the solute standard state. So let's think about what that is. This magnitude is Henry's constant, and of course it's a fugacity, and has units of pressure. So it is the Henry's constant, but if we stated in words what the solute standard state is, it would be the fugacity of a hypothetical Henry's law solution of 2 in 1 when x2 goes to 1. So that's what's embraced here in the diagram, but that's what it would be if we wanted to state it out in words. So we've got these two standard states to consider. Now as we move out from either of the ranges, the Henry's law range, we move out here, or if we, actually not only if we move out here, but from the standpoint of ordinary solutions, we want to describe the whole composition range. We use so-called modified equations. So what I have now, again, is the modified Henry's law. Which we then stick in the fudge factor, let's say F2